so much of the format of the models we take is like exactly the same. It's just
What, like utility management?
yeah, it's all the same. It's just Lagrange. It's just different, maybe a different budget constraint, or like maybe a different like endowment, whatever.
I mean, it's definitely worth memorising proofs and stuff like that. Memorising optimization. And then
I suppose, but you did say that we weren't going to get many proofs, but then you said you were going to pass paper, and it was like some previous questions like that.
Yeah, there was stuff we don't know.
He said explicitly, he's not going to put first work on as well.
Okay, questions on what we did yesterday?
No? Okay. All right.
And since you weren't here at the beginning, just to say, starting a couple minutes late, but I announced right at the beginning, I try to start at 5 past and end at 5. Yeah, so that's, other than that, there are no restrictions in terms of coming in, going out, etc. Yes, you need the code. One seven five 765. Now, about the work that you submitted, a lot of people did submit, just about everyone. It's good. I'm going to try and mark them today, and I will do one of the following. The plan is to return a photocopy to all of you of the work that you've done, preferably on Thursday. That might not be possible for me to do. In which case, I will bring the marked work. You could see it while I work it out on the board. I'll take it back, and then I'll give you photocopies of your work. Is that okay? So just to make sure that you have access to what you handed in, together with, you have access to that anyway, the PDFs, but together with my scribblings on them. All right, so the last thing that we saw yesterday was we looked at, so this is the simple model. And the last thing we saw was I drew a figure with the consumption choices to be made by a young agent. I drew it as a single budget constraint, but of course, this is an economy with money. In the absence of money, as we saw right at the beginning, gain down could be the only possible outcome. But with money, things are different. So I drawn a budget constraint somewhat like that. I'd marked prices and things if I remember right. But we'd also seen what the stationary competitive equilibrium is. And at the stationary equilibrium, okay, equilibrium, which for us is always stationary, so I'm no longer writing that. Stationary equilibrium, prices were constant. And therefore, your budget line would have slope 1 or minus 1. So the equilibrium consumption for any agent would be the point at which their utility is maximized subject to that constraint. Correct? At some point over there, shall we say, that was your equilibrium. Is it okay? Yeah? Now, we want to set up a new problem and talk about something called the Planner's problem. Now, Planner's problem can mean all sorts of different things. For us, we are looking for, since our equilibrium is, we're looking only at stationary equilibria, for our Planner's problem, we want to ask, suppose you had someone who acted on behalf of everybody in the economy, and they are asking what is the best feasible stationary outcome. Okay? So that's what the planner is going to choose. So best for us is in terms of preference, of course, or utility, the way we're thinking about it. Best stationary outcome. So let's start with our feasibility condition, which is consumption by the old agent. They were born at t minus 1, so at period t, their consumption is denoted C2t, plus consumption of the young agent, who's young at time t, cannot exceed the total endowment at date t. That's the feasibility constraint at every day. And you notice this line has slope minus 1. Okay? So, impose. Okay, so that's feasibility. So when you impose stationarity, which is what you wish to do, because we would like the allocation to repeat over time, you impose stationarity, so consumption by the old and the young are both independent of time, and you get that constraint. And so your problem becomes maximize. You can write it in either of two ways. I'm going to write it as choosing C2, but it does not have to be that. C2 has to be non-negative, but over here I'm dropping that requirement. These are some things that we've already understood. So U of, well, from there you get Y minus C2 and C2. Is that okay? So that's going to be the way we define our Planner's problem. That's not the only way you can define a Planner's problem in this economy, but this is, when you look at stationary solutions, that's really defined, and it has a name. Solution is C1 GR C2 GR. It's called the golden rule. A very important concept here. Okay, the idea being that it's the biblical golden rule, right? Do unto others as you would that you want to you. Same thing here. So you find the consumption point at which you expect everybody else to behave the way you are behaving, or you behave the way everybody else is behaving, in order to come out with an outcome which is actually a nice one. A nice one in terms of giving you the highest possible utility in terms of allocations that are stationary. Okay, so the first order condition here is just one variable, so this is easy. The first order condition becomes U sub 1 Y minus the solution, which is C2GR. C2GR. So we're looking at the value that satisfies the equation, which I have put on the board. 2 solution to that equation is the golden. And I'm not going to work any of these out on the board, but of course, problem set will give you a few exercises to get so that you can get some practice on this. So this is in the simple model. Okay, the solution to that equation is the golden rule. Is that okay? It's just a first order condition from there. Finds C2GR, and then from the feasibility constraint, you work out what C1GR is. Now, we are not proving this. It's not easy to prove. can be done even at this level, but it takes time and I wouldn't want to do that. We're not proving it. However, it can be shown that the golden rule allocation is a Pareto optimal allocation in this economy. Yeah.
Wait, sorry, when you put the subscript 1, 2,
Yep.
is that with respect to 1, 4? Is
Here
it,
and here?
yeah.
Yes, those are partial derivatives with respect to the first and the second
And
order.
there's a common utility function for both of the...
Yes, the assumptions, sorry, you were not in class yesterday,
Yes.
but the deal is that you have an economy that goes on forever, starting at time t equals 0. Nothing really happens at t equals 0 except some agents are born who are active from date 1 onwards. Date 1 onwards, you have people who are born and they live for 2 periods, but you also have this initial generation that was born at date 0, but they're active only at date 1. So in every generation, at every date, you will have young and old agents who are contemporaneously alive, and they will trade. There will be just one good at any given date, and there is no production, like what you saw in macro. Okay? And the endowment structure is very special. The young agent has Y units of the good, the old agent has nothing. That's the endowment structure. And agents are identical across time. You might have many agents in a generation, but they're all the same. However, you have the young and the old, and they behave differently, depending on prices that they face. The utility function is, since agents are identical, it's the same utility function for all the agents. And that would be the first one. Yesterday, we also looked at the monetary equilibrium, which you could look at yourself and ask if you have any questions. Is it okay so far? Yeah? So, the golden rule can be shown to be Pareto optimal. And there are many Pareto optimal allocations in these economies. Lots and lots of them. But this is a nice one, which is why we focus on the good. I repeat, showing that it's Pareto optimal is not trivial. It's not this is not a Pareto problem. We are looking at a representative agent here. While the economy, even if you have just one agent being born in each generation, has an infinite number of agents. So, dealing with that, you can deal with it by assigning Pareto weights, but for the problem to be mathematically tractable, if you take that route, the Pareto weights have to be such that they decline over time. Otherwise, the problem is not tractable. Of course, that would pick out very special Pareto optimal allocations. So if you want to look at the general problem, it needs to be tackled in a completely different way. There is a way to tackle it. It's been known for a good 50 years, but it's a non-trivial problem. So that's all that I'm going to say about that. But the thing to observe here is, look, the constraint that we have in the figure there is exactly this one. That's a line of slope minus 1, that's a line of slope minus 1 with inequality. The aggregate resources are y, aggregate resources there for the agent are y and 0, so y, right? The utility function is the same. So the first order condition is the same in the two problems. But therefore the solution must be the same. So we've shown that in the simple economy, introducing a constant money supply and looking at stationary monetary equilibrium give you a nice outcome. It's exactly the golden rule. Is that okay? Now, if you have such a question on the exam, you won't get full credit. If I ask you to compute the stationary monetary equilibrium, you work out the golden rule and say it's the same. You will get some credit if you've made the argument correctly, but that's not the way to do it. If I asked you to work out the golden rule, you work out the golden rule. If I ask you to work out the stationary monetary equilibrium, you work out the stationary monetary equilibrium the way I've shown you to do it. Is that okay? But the point to be made here, I repeat, yesterday we worked out the stationary monetary equilibrium. We noticed that prices will be constant. Therefore, the consumer, any consumer, is solving a problem where their budget line is slope minus 1. And it goes through their endowment. And they satisfy the first order condition, which geometrically means they're picking the point at which they have a tangency. If you define the golden rule problem here, it's exactly the same problem. And therefore, it must have exactly the same. And therefore, the conclusion is, in a sufficiently simple economy, introducing a constant amount of money allows you to obtain not only trade, but a Pareto optimal allocation. Is it okay? Yeah? So now we're going to move to the next model. Again, step by step, repeating the steps that we used yesterday, except our solution will of course be a bit different. So the next one is variable population. Of course, we won't be looking at general variable population, although you could. Not if you want to get a stationary equilibrium, but in general you can have an economy in which population changes in a very general way. We will be looking at the particular case where the population grows geometrically. It could contract also. Okay, so population, the number of initial old people will be set equal to 1, that's without loss of generality. And then from then on, the population changes at rate n. And this is for all other t. And n is positive. The population cannot become negative, but n does not have to be larger than 1. Okay? So now in a competitive equilibrium, so the problem that any agent faces in equilibrium or otherwise, the agent's problem, as yesterday, is actually the same problem as yesterday. Because from the agent's perspective, nothing has changed. If prices behave differently, the agent will respond differently. That's a separate matter. After all, the case that we had first is the particular case when n equals 1. So you would expect some commonality. But other than that, the agent's problem is exactly as before. So C1, 2, T, C2, T plus 1, T. 3 numbers that are non-negative. Maximize the utility, C1T, C2T plus 1. Subject to what they spend when young plus any money that they carry over has to be less than or equal to the value of their endowment, and what they spend when old has to be financed from the money that they carried over. Exactly the same as yesterday. You should check. More importantly, you should be able to write this out on your own. You should understand what you're doing. You shouldn't have any problem in that. If you do, you need to ask me. There's something to have understood. Okay, so dot, dot, dot. And we get the first order condition as yesterday, where we need to verify non-negativity, but we can do that later. Okay. I didn't say this yesterday, but since there's a positive amount of money in the economy, at equilibrium, people will carry a positive amount of money. For the money market to clear. They all behave, all young agents behave in exactly the same way. And therefore, since they carry a positive amount of money, that ensures that consumption when old is positive. And since they carry a positive amount of money, over here, unless C1T is 0, from there also you will get something that's positive. And this you will typically get from properties of the utility. All the examples that we look at, you will not end up consuming 0 at any rate. Okay. So your first order condition will be U sub 1 y minus mt pt, and then when old mt plus 1 pt plus 1 minus 1 over pt from the chain rule plus u sub 2 y minus mt over pt mt over pt plus 1 equals 0. The minus sign is the one that was relevant there. The brackets here. Exactly the same as yesterday, because nothing has changed so far, at least from the consumer's point of view. What changes is equilibrium. At equilibrium, well, we still have capital M as the amount of money. Okay? Each agent will demand MT, which depends on prices PT and PT plus 1. Okay? However, we don't anymore have just one agent. We might have a different number of agents. So in general, it will be the population that we have at time t, and at equilibrium, we put stars on the prices. Okay? Yeah? So the total amount of money has to be held by the population that we have, which might not be just 1, because n could be different from 1. Now, of course, with the framework that we have here, the number of people that we will have is, so that I don't have to write it again, little n raised to the t. Is it okay? Yeah? Yeah. Okay. So now, again, so that I don't have to write everything again, I'm going to make changes over here. In the notes, etc., you have all this stuff worked out carefully. So the amount held by each agent is capital M divided by n raised to the t. Is that okay? And therefore, my first order condition at equilibrium becomes, I have capital N there, divided by n raised to the t, p star t. Is that okay? Look at it. I had the money demand, which at equilibrium is capital M divided by n raised to the t. Therefore, I can replace all of these by, did I put m raised to the m over t plus 1 here? If I did,
Yeah.
that's a mistake. It should be m sub t.
Just no plus one.
Okay? I'm sorry, I didn't notice that I written that. It should be m sub t. The way it is over here. So here it would be capital M divided by n raised to the t again. And here I get p star. Here again I get p star. I get p star, capital M, little n raised to the t, capital N, M, little n raised to the t, p star, p star.
Are we just assuming that's like a black box?
Sorry?
Are we just assuming that's a bit of a black box?
Which one?
MT, just some function of PT and PT.
No. So this again, this was discussed yesterday. So when you look at the first order condition, the one that I had before without the substitution, that is a single equation in three variables: mt, pt, and pt plus 1, regardless of equilibrium. This is the first order condition.
Right.
And therefore, I can, under very standard conditions, I can solve for mt as a function of pt and pt plus 1. That's my money demand
Do
function.
we know what that function is?
Sorry?
Do we know what that function is?
For any given economy, you can work it out.
Alright, so it's just, it would be
It's
something.
the implicit equation that solves that equation. It's an implicit function.
Okay.
Okay.
Then it's not.
Yeah. So if I give you any example economy, you can write down the first order condition, and if you wish to, you can work out mt as a function of pt and pt.
Right, okay.
I give you a messy economy, it could be a bit of a mess to work out, but I won't give you a messy. And you don't need to work it out explicitly. The reason being, this trick shows you that you don't, because our economy is sufficiently simple. Since the economy is sufficiently simple, and we are focusing on equilibrium, you can use that property to actually say, well, I don't need to work out the details of the money demand.
Right.
And, if you wish, you can. You don't need to. Is that okay?
That's fine.
So that's equilibrium, which makes our first order condition a lot simpler. But of course, that's not the end of it. From the budget constraint and stationarity, etc., we want the stationary solution, and therefore C1t will be some C1, C2t will be some C2. Whether I write t or t plus 1 doesn't matter, right? Because I want every agent's consumption when old to be C2. So whether I say that C2 at t is C2 or C2 at t plus 1 is T2, say the same thing. These are different agents, but they all behave in the same way, under stationarity, in terms of their consumption. Okay, and from the budget constraint, when young, that we have over here, we know that mt over pt equals y minus c1t. Okay. So, imposing stationarity on the budget constraint. This is why all the steps are important. Stationarity, the budget constraint becomes divided by Pt equals y minus C1, okay, which we define to be mu. All this is just as we worked out yesterday. So mu is the definition of y minus C1, or mu is defined as y minus C1. At equilibrium, of course, you will get a particular value. Okay? So now impose equilibrium. So now it's a stationary monetary equilibrium. So at equilibrium, you know that MT has this special form. So you get capital M divided by N raised to the T, P star T equals R mu star. We don't know what mu star is, but we'll work it out. Is that okay? Yeah? Tim? Yeah. Go on. You need to follow. It's all. This part of the problem is it's all in the notes.
Yeah.
So when you read it, it looks like you've understood everything, but actually you have understood nothing. You need to work it out yourselves as well. So what you're doing is exactly the correct thing. So ask me if there is something that's not clear.
It's just where the
Yeah.
budget constraint came from.
Sorry?
The stationarity thing.
But where does that come from?
But that's fine.
Yeah.
Underneath it, directly underneath it.
This is just the budget constraint.
Yeah. Right.
Right? So now if I impose stationarity,
Yeah.
which is what I wish to do, I impose it on the budget constraint,
Yeah.
right?
Which
So then the budget constraint, the right hand side becomes y minus C1.
Yeah. And
These are endogenous.
right. So we can't get.
We will.
We will.
But at this stage, I can't simply say this is constant, that's constant, we're the wrong answer, you do that. Don't do that.
That makes sense.
Okay? So C1 is a constant. Give this, the part on the right hand side, a name. So give it name mu. Just call it mu. Now, at equilibrium, mu will take a particular value, which is mu star. And on the left hand side, Pt will take the particular value P star T. And Mt at equilibrium will take the particular value, capital M over Nt. So this is your equilibrium condition. When you look at a stationary monetary equilibrium. Is that okay? Yeah? So, it will be a bit of a mess, but I would like to keep this on the same board. So let's move from there to there. Now, hence, one of the things that I wish to work out is the relative price. So over here in the first order condition, I have the relative price. So I need to work out the relative price, which was 1 over there. Okay? You might expect that something or the other is going to change here. You don't want to make any assumptions about what's going to change and how. You want to work it out. Right. So from there, from your equilibrium condition, you know that P star T equals capital M divided by N raised to the T mu star. Correct? So, P star T plus 1 divided by P star T will be capital M divided by N raised to the T plus 1 times mu star divided by capital M over N raised to the T mu star. Do not get tempted and write down the answer directly, because chances are you will make a mistake. Please die over it. Okay? So it's better to write it out. Even if you've done this many times, just write it out. It takes you another 20 seconds and you get the correct answer. And now you can simplify this and your answer is 1 over N. So when N equals 1, the relative price is 1. When N is not equal to 1, the relative price is not 1. What does that mean? Is something that we'll come to in a moment. So we know what the relative price is. Okay? So now, how do I solve for the competitive equilibrium? I'm assuming you'd rather not have me change things here. Should we leave that the way it is and write it again? At equilibrium? So let's do that. So, U sub 1 y minus, well, m over n raised to the tp star t is exactly mu star. That one's all right. M over n raised to the tp star t plus 1, what's that going to be?
Still u star.
You sure?
Times 1 over n.
So check it. Okay? So what are we going to get? Let's write it here. So we wish to work out is m over n raised to the t star t plus 1. This is what we need to work out. Correct? So this is m over n to the t, and p star t plus 1 we know from there, okay? But I need to write it in the denominator. M divided by n to the t plus 1 you start from there or there. Is that okay? I'm replacing p star t plus 1 by m divided by n raised to the t plus 1 mu star. Yes, no, maybe. If not, please ask. But I can tell you why. So I've rewritten my equilibrium condition by putting p star t on the left, but that's true for every t. So at p star t plus 1, I simply get n to the t plus 1 over there. Nothing else changes. Which is n times. I don't know whether that is what you were saying, but you might have been.
No,
You were saying 1 over n.
yes.
Is that okay? Work it out and you'll be fine. Don't jump, don't guess, don't do the things that you were taught in school from the time you were 3 years old. It's a bad way of doing maths. It's a terrible way of doing maths. Quick. Everybody's jumping around, and all the way till the end of your life, you'll be making mistakes. Don't do it. Understand what you're doing, take an extra minute, you'll be fine. You could get it wrong, of course you could get it wrong. But if you guess, the chance that you get it wrong even more often, right? So this is n times mu star, and on the right hand side, I'm going to write it as, it doesn't matter as to how you write, well, you're going to have pt star over pt plus 1 star, p star t plus 1, which is the reverse of what we have there. So it's n, and then the consumption bundles you've already worked out. That's an equation in one variable, which you can solve. And it agrees with what we saw yesterday. When n equals 1, it's exactly the same as what you had before.
Sorry, how come we've got differentiate with respect to u1, sorry, 1 twice?
Sorry, because that's repeated. Thank you. Is it okay? All set? Yeah? Very good. So now in this case, the agent's problem I'm not labeling the figures, but you're right. But depending on what line I put in, the agent will give their optimal consumption, right? So we are saying that, so what would you expect to happen here? Let's think of the economics here. I find it easier to make that connection very often. So if you have a growing population and you're looking at a stationary monetary equilibrium, the money supply is the same. More people are using the same amount of money to buy the same amount of the good. Their trade, if you think of the trade, right, since it's a stationary monetary equilibrium, the old agent is always buying C2 units with the amount of money they have. The money supply is constant, the price better be increasing with an increasing population. So you have deflation when you have an increasing population, you will have inflation if you have a decreasing population, even though the money supply is constant. First lesson that we learned from the overlapping generation. The fact that you have A population that can change over time means you can get inflation or deflation even though the money supply is constant. Something which Friedman, in general he's right, but he would have told you that inflation is always a monetary phenomenon. It's not. Population growth is going to give you, at stationary monetary equilibrium, it's going to give you deflation. Is that okay? The first lesson. Right. So now, you're going to have a solution here. Okay. Now let's think in terms of the planner's problem here. I'm going to get back to that. I'll get back to that a bit later. Or if you wish to, we could actually do it now. So if n is larger than 1, if you have a population that is growing, right? We said that that converts into the equilibrium price level falling over time, right? Therefore, if you look at a constant price ratio in which the price tomorrow is lower, that means that you can afford to buy more tomorrow. So you get a line with a slope in absolute value which is larger than 1. Okay? I'm not going to ask you to do anything bigger than the exam. This is why exercises will be algebraic exercises. So that you actually work things out in detail. You don't need to jump around. Yes. Intuition is something that you need to develop. And you need to understand the geometry of what is happening, etc. to clarify what is happening. The way to solve problems is with the algebra. Okay? So now let's relate that to the planner's problem. Now we are going to have, it's no longer the simple model, so I would, so planner's problem, variable population. Yeah. Okay? So, things will change here. What's the feasibility now? The number of old people at time t is the number of people who were born at t minus 1, which is capital N t minus 1, plus the number of young people who were born at date t, nt, plus resources, well, brought only by the young people, so nty. Is it okay? Now, the number of old people in our framework is lowercase n raised to the t minus 1. The number of young people is lowercase n raised to the t. And the number of young people here is again lowercase n raised to the t. So I can simplify and write it in that form. Okay? Will that go too quickly for you? Is it okay? Yep. So, when I impose stationarity, I get this in the form C2 plus n times C1 is less than or equal to n times y. Yeah? If I represent that over here without writing it with the t's, so C1 and C2, that point becomes 0 and y. If I consume nothing if I give nothing to the person who's young, the person who's old gets n times y. Right? Now, careful, this constraint refers to agents across time. These are different people. But since everything looks exactly the same from period to period, I can actually use this figure so long as I interpret it correctly. So I can think of it as solving the problem of the same person. Young and old. Why? Because when they're old, the consumption that they get is exactly the consumption that the person who's contemporaneous with them, but old when they are young, will get. So I can use the same figure. Is that okay? So, how do things change here? So my maximization problem, since I'm writing everything in terms of C2, my C1 will become y if you get confused because I keep erasing things and I make changes on the board, tell me. I can always write things separately. If it's getting confusing, please tell me. Is it okay so far? Right. So what we did here is rewrite the feasibility constraint for the case in which we have a variable population. Right? So I would have had capital N sub t minus 1 because that's the number of old people. They were born at t minus 1, so the number of old people at time t is capital N t minus 1. And I would have had capital N sub t here and capital N sub t over here as well. But my population is growing at a geometric rate. So the number of people at time t minus 1 would have been little n raised to the t minus 1. Little n raised to the t, little n raised to the t. So I can simplify that and write it in that form. So once I impose stationarity, that becomes my constraint. Okay, so now we don't need that problem anymore. So leave it there. My problem becomes maximize by choosing C2. You, what is C1 now? C1 is y minus C2 divided by n and C2. So my solution solves what first order condition? So let's get the first order condition from there. U sub 1 y minus C2 gr divided by n C2 gr. Use the chain rule, minus 1 over n plus u sub 2 y minus C2 gr by n C2 gr equals 0. This is what we should do. Is that okay? Yeah. Minus 1 over n. Here, if you write it as p star t plus 1 over p star t, minus 1 over n. You get the same slope. Same argument as before. You're going to maximize at a point somewhere over there, which is going to be a GR, and by the argument that we've made, you're solving the same problem with the same constraint, and therefore it is also your stationary quantity. You get inflation, you get deflation, who knows what, but you're still hitting a nice outcome. Is that okay? Anything that's not clear? Anything at all that we've done so far? Things will change from now. Okay, we've had two nice outcomes, which is all very good. We don't go home saying that everything's fine, because everything's not fine. All the interesting stuff is yet to come. This is the easy stuff. This is what people would typically teach you on the OLT and say, okay, now you can go. That's no way of doing it. Anything that's not clear? Anything at all? Since I saved some time in the way I wrote things on the board because you were kind enough to let me do that, we have a bit of time on hand. I'm happy to. Yeah.
There's no constant price in this model. There isn't a constant price.
So, in the model with a variable population, if you look at a stationary monetary equilibrium, the price will not be constant. Now, I can frame your question in a different manner, which is there an equilibrium with a constant money supply, with a constant price?
Yes, that's what we did first time. Not with a very
No. Be careful. Now I want you to think of it differently. You are mixing this in with what we saw in the Bewley model. In the Bewley model, our focus was asking if we insist on stationary consumption, right? What must the situation look like? And we saw that you cannot get an equilibrium. Then we said, Suppose you look at constant prices and you want an equilibrium. What's a simple equilibrium that you can get? And that's the one that we found as a monetary, not stationary, right? The consumption was fluctuating between two values. Over here, in the first model, we said we want an equilibrium with a constant money supply, and in equilibrium, we want consumption to be stationary. And we found the implication is the price must be constant. Okay, so what? Yeah. In this model, we've said now we have a variable population. We would still wish to find an equilibrium in which consumption is constant, stationary. And we see that then prices have to change.
Yeah. So it's good.
There is no apologies here. You're trying to understand things. If you don't ask questions, you will not understand it as well as you actually can. This is what you should be doing. Asking questions, probing. What is it that you do? This shows that you're engaged. That's much more important than anything else. Is that okay? Anything that's not clear? How we work out equilibrium. So what we will do next? And there'll be no exercise on this. So on Monday, on Thursday, I'll be going over the coursework. On Monday, we will talk about a model of commodity money. If you read the press, very often you will find these, I call them, you'll find a lot of people telling you, the whole problem in the world is central banks print money and that's a bad thing. We should just go back to the gold standard, etc. Sounds like a very reasonable thing that they say. Then you have other people who say, oh, Bitcoin is a great idea. I'm not going to talk about Bitcoin. I'll only tell you that in the way we define fiat money, Bitcoin is actually private fiat money. That's what it is. It's all, from what I understand of it, it's private fiat money. Just as the price of fiat money can fluctuate over time, you haven't seen that in any great detail. But the fact that it's traded tells you that that can happen. And since it's fiat, there's nothing pinning it down. And the same thing happens with Bitcoin. That's why lots of people who make money on it tell you it's a great idea. Except when they lose money, then they keep quiet. So of course, it's like anything that you want to go to the casino and speculate. Your income, your wealth, you do what you want to with it. It's not the same thing as saying it's a good idea. There are lots of regulations on betting in many countries for various reasons. So that's Bitcoin. Now, when it comes to commodity money, which is what gold would be, we will study a very simple model of commodity money, and we will show that any commodity money equilibrium is not Pareto efficient. So for us, that's the key idea. You replace it with whatever you want to, you will keep getting the same problems. In the real world, commodity money, which was essentially the gold standard, was given up in the late 60s, early 70s. Okay. Because prior to that, everything was done through the US dollar and pegging it to the price of gold, etc. Currencies were pegged to the US dollar. That created problems in terms of imbalances across countries. It was I'm no expert in any of this, so I don't want to say any more than that because I get it wrong. That's not to say that most people get it right. International finance, this stuff is complicated enough. It shows you why this stuff is non-trivial. This is why this stuff should not be given to babies. You need to understand it from the basics and understand why there is a problem. You might not know how to solve it, but at least you will know that there is a problem. All these things become more and more complicated. You just have some big guy from an investment bank and telling you, no, this is fine. Or you know the person was a basketball player and they got into an investment bank. Famous case being the chap who used to run Lehman Brothers. So you basically have no background in terms of formal training in economics. Lloyd Blankfein, very well educated, etc. He was a lawyer. So that's not to say that they can't do their job well. I'm saying something completely different. What I'm saying is, if you actually want to understand these things, you might say this is all esoteric academics. It is. But it makes you realize that you probably want someone there in Bernanke who wasn't a theorist, but at least he knew enough to understand that there were questions that you need to be careful with. That's good enough. So long as you don't have somebody, Trump being a great example, just walks in and says, I have the intuition this is the correct thing to do. Don't do that. The last thing you want to do. Okay, so that's what people see on commodity money. A very clear way of understanding why commodity money will give you outcomes that are not very efficient. That's good enough. That's the next thing that we will do. And after that, we will look at models in which you have other variations, including the possibility of government expenditure and how you finance it. And with this very simple model, we will be able to see a little bit about what happens. Okay? We stop here then. Thank you very much.
That's all right.
Yep, see you on Thursday.
Sure, sir.
Okay, bye.
Thank you.
Bye.